Hello and welcome to this video about nilpotent matrices. A nilpotent matrix raised to the power of a finite number will be the zero matrix. A standard basis nilpotent matrix will look like this. There will be a mixture of ones and zeros along the diagonal above the main diagonal, which is called the superdiagonal. They could just as easily have been placed in the diagonal below the main diagonal, but it's standard to put these ones and zeros in the diagonal above the main diagonal. Multiplying this matrix by a column vector will shift its elements up and replace some elements with zeros. The minimum power required to make this matrix the zero matrix is called the index. You can see here how multiplying them together will eventually make them zero, because this diagonal will be shifted to the upper right corner and obtain more zeros along the way. We can write this equation using power notation, and we can see that raising it to the third power or cubing it will be enough to make it into the zero matrix. So we can say that its index is 3 because of this. If we conjugate a nilpotent matrix by a change of basis matrix, it's still a nilpotent matrix. So we'll just prove this. We'll start with this expression and expand it out. It should give us the zero matrix. We'll use under bracket times notation here. We can gather all of these matrices with their inverses together, and they'll all be equal to the identity matrix. And they'll all multiply by the matrices to the right or left to give us the nilpotent matrix raised to the power of m. And this will give us the zero matrix, so that's this fact proven. The identity and zero matrices will be the same in any basis, and all of the eigenvalues will be zero. This matrix is already in Jordan canonical form and can't be diagonalized, but it can be easily manipulated by functions in this form. So let's look at this nilpotent matrix that has all ones in the superdiagonal. It requires the highest power of m, being equal to n in this case. Squaring it shifts the diagonal like this. Now there are less ones. And here is its square and cube. And here it is raised to the fourth and fifth powers. And finally here it is raised to the sixth power. And this is the minimum power necessary to raise it so as to get the zero matrix. So its index is 6. Now to look at some code. This function tells the user if this matrix is a nilpotent matrix. We'll declare the function with all of its internal variables. A matrix must be a square matrix to be a nilpotent matrix, because it has to be able to multiply by itself. Now we'll raise this matrix to the power of the number of its rows or columns. This should give us the zero matrix if it is nilpotent. We'll check here if this matrix is equal to the zero matrix. And this Boolean variable should be true if and only if this matrix is nilpotent. Now we'll study how to raise a matrix to the power of an integer. We'll declare this function. And so we'll only do this function if the matrix is square. Raising a matrix to the power of 0 gives us the identity matrix, because it behaves like the number 1. And is the matrix equivalent of the number 1. Raising a matrix to the power of 1 gives us this matrix itself. Raising a matrix to the power of 2 or more requires a loop, so we can multiply the matrix by itself over and over. We'll copy the matrix A to matrix B as a sort of storage. It'll initially be A. This is the loop where we'll multiply the matrix by itself n times. We'll multiply these matrices to get the next power of matrix A. We'll store this next power of A back into B. The final answer will be in both B and C. So here's another function that can calculate the index of the matrix if it's nilpotent. It's faster because it won't do more multiplications than are needed. And this matrix must be square to be nilpotent. We'll set the main Boolean variable to be false, so that we can enter the main loop for the first time. We'll use B to store matrix A to the ith power as we go around the loop, like before. So it is initially set to A to the power of 1, which is A itself. We'll make a loop to cycle through the number of rows of A times, or until A is the 0 matrix, because we'll continually check to see if it's 0. I is the main counting variable. We'll multiply A by B to get the next power of A. We'll firstly get the first element of this matrix, and then get the absolute value of it. And if it's close enough to 0, we'll check the rest of the matrix to see if it's 0 too, and the Boolean variable will be set to true if it is. We need to copy this matrix back to B if we're going to continue going around in the loop, so we won't copy it if we leave the loop, to make this function faster. And so if it is nilpotent, we'll set this global index variable to be this value of I. And then we'll return this return variable here, which is true if and only if this matrix has been found to be nilpotent. So now to construct a random nilpotent matrix to test this function. This function will create a standard basis nilpotent matrix. We'll set the rows and columns here. Then we'll fill the matrix with zeros. We'll calculate the number of zeros and ones in the superdiagonal here. There should be at least one 0 and at least one 1. We'll place the zeros in this array, followed by some 1s. These haven't been jumbled up yet. I put these two numbers in the array to test the function and debug it. It's a good idea to do this while constructing the function. So now we'll jumble up this array. I've already done a video about jumbling up numbers. And then we can place the contents of this array into the superdiagonal of this matrix. We can make up this function to create a random non-standard basis nilpotent matrix by conjugating it by a change of basis matrix. I've gone into more detail on how to do this in my video on projection matrices. So we can modify this function a little bit to create an only just non-nilpotent matrix by adding a random non-zero number to the diagonal. So this function adds a random non-zero number to the diagonal. It's pretty simple to understand and doesn't need much explaining. So I hope that you have found this video helpful, insightful, and maybe even interesting. Please click like and subscribe if you did. Feel free to share this video, and please leave some helpful thoughts and criticisms in the comments. And thanks a lot for watching.